Hi everyone, welcome back to our class. So on Wednesday's class, we finished 10.2 and started 10.3, but we haven't done a lot, so we'll continue with it. 10.3 would be another hand of 10.2. So 10.2, we've had something called, what's the name? It's called the pooled t-test, which we're assuming that the population standard deviations from the two cases are equal. 10.3, well, we do not assume. So standard deviations not assumed equal. So this is more common cases because in the reality, we don't really know our sigmas, the true values of standard deviation for different populations, right? So we start from the very beginning of this chapter where we're going to derive the statistics formula. The first one is what we're looking at. So 10.2, the pooled t-test are coming from, we assume sigmas are the same. So sigma 1 and sigma 2. And because they're the same, so it will become sigmas. Common factors, you could plug it out of the square root. So it will be our test statistics for the first case. And now we keep it as what it is because we did not assume sigma 1 and sigma 2 are equal with each other. So now we simply use the sample standard deviation to replace it. According to some theories of the statistical methods, we find the fact that for the non-pooled t-test, the following test statistics are following t-distribution. Now this is exactly what we've had here. It is following from the distribution of t with degrees of freedom of delta. So this is a weighted average of, related to the variance. Standard deviation square and that's variance. This is the two different variance of two different populations. And the important thing I want to emphasize here is we have to round it down to the nearest integer when we're calculating the weighted degrees of freedom, right? It's different from what we've had. Well, I remember we had this when we calculate the minimum number for the sample size, right? We are going to round it up for the sample size. But here, degrees of freedom, we're going to round it down. That's a key part. The procedures for non-pooled t-test are quite similar with what we've had for the pooled t-test. Slightly different. The first one is the assumptions. Pooled t-test has 4 assumptions where we keep the same simple random sample, independent sample, normal distribution, or large samples. The fourth one would be assume that standard deviation are equal. But for the non-pooled t-test, we don't. Step 1 is the same. We have 3 different cases, two tail, left tail, and right tail. Step 2 would be gonna decide the significant level alpha from the problem. So sometimes they will say, hey, this is the significant level. Okay, got it, directly use it. If they're saying the confidence level, then alpha would be 1 minus your 90% confidence level, then 1 minus 0.9, 0.1. 95% confidence level, then 1 minus 0.95, then that is 0.05, right? And step 3 is the test statistics. So this format and the fact, right, coming from the fact, why we do not have the same numerator, because denominator keeps the same. You can tell s1 squared over n1 plus s2 squared over n2 square root. This is the same as s1 squared over n1 plus s2 squared over n2 square root. The numerator are different because in our case, right, if you're trying to minus mu2 on both sides, Left side will become mu1 minus mu2 equal with 0, right? And the right side of those non-equivalent sign are zeros as well. So it is the same, but we just assume mu1 equivalent with mu2. This is a minus 0 on this part, and then this part is gone. So what we've got is simply x1 bar minus x2 bar. This is how it comes from. That's step 3. Step 4 and 5 would have two different approaches, right? Left side is critical value approach. And the same, we have rejection region, non-rejection region, rejection, rejection, non-rejection, non-rejection, and rejection regions. And those are solely related to the types of our alternative hypothesis. And how we're going to find this is when we fix our alpha, you're going to use the table to figure out the t-score. And note, we had special cases. We had a lot of examples in class saying that how to find a negative value of T alpha, right? Because the table only provides you the right side positive values for T-scores. So if we have to find on the left side, you're going to do some transformation according to the symmetric properties. The same with the p-value method. And in both cases, we have to recalculate the degrees of freedom. The difference between the non-pooled t-test and the pooled t-test is the degrees of freedom is not anymore 1 plus n2 minus 2. It's much more complicated, and remember to write it down to the nearest integers. P-values, the criterion for p-values would always be the same. It doesn't matter the non-pooled, pooled t-test, or the one mean, so something that we've learned in chapter 9, the one mean z-test, the one mean t-test, all of them are the same. So you would reject the H0 only if your p-value less or equal than your alpha, otherwise do not. And don't forget to interpret the hypothesis after you've finished one. If our homework or assignments or final require you to do so, okay? You have to complete, like write an entire sentence. Do not just simply say, hey, I'm going to reject H0 because of above. No, that's not acceptable. And another thing related to that is the confidence interval. So this confidence interval related to the non-pooled t-test is coming from our two-tailed hypothesis testing, right? I remember I've introduced the similar stuff when I talk about the pooled t-test. Step 2, this formula first part is the guess of your mean. Not the mean, it's the difference of the mean, right? The guess where it locate. In the second, plus or minus, the second part is your margin of error. This margin of error comes from the step 3. The t-score multiplied by your pooled, non-pooled t-test standard deviation. It's a weighted standard deviation. And then the t-score is not anymore t alpha, but you have to write down a t alpha over 2. This is fixed. So it doesn't matter when we say the z confidence interval or t confidence interval, the subscript under that t or z would always be alpha over 2. Because when we find a confidence interval, you never know which direction your answer would be shifted, right? It can be less than what I guess, or on the right side of what I guess. So what we're going to do is we'll make it equal probability. It can be either left or right 50-50%. So you would have t alpha over 2 as your t-scores, put it here. And the assumptions keep the same. Okay, then we will use example to finish the material. So now we're trying to perform a non-port t-test about operative times with two different systems. So they're saying scholars from Arizona State University, professors, that they are trying to obtain the data displayed in the table. Those are our operative times in minutes for two systems. One system called dynamic system, another system called static system. And the question is, at the 5% significant level, do the data provide sufficient evidence to conclude that the mean operative time is less with the dynamic system than with the static system? So the key information we could find from this question sentence would be, first, significant level, right? And we would have alpha equivalent with 0.05, directly tell you. And then this less than give me the idea of our alternative hypothesis would be the less sign. Okay, keep this in mind. I wrote it down on my pad that I will show you how to finish these procedures. And then based on the table, I definitely can calculate some statistics, like basic statistics according to the table. We could find X bar, X2 bar, and then S, the standard deviation of those two population, those two samples, sorry. And then the sample size, 14 and 6. So I've wrote it down. Let me double check. Yes, this is what we've got. And then before that, you might need to check the normality according to the QQ plots or the box plots. And in our case, this is proof that we could use the non-port t-test. Now I'm going to switch to my pad. And then I'll write it down what we will need. So this is what we've got. I've just wrote it down when I trying to rate it. I've wrote it down. So this is our dynamic. And this is the static case. And then we got those basic statistics data. And alpha equal to 0.05 is something we've got from the question sentence. Dynamic here, less or equal than is the question sentence where it comes from. And if you remember for the step 1, right, you're going to say let mu1 denote the mean operative time of the dynamic system, and let mu2 denote the mean of the mean operative time of static system. So this would be the definitions that you have to give if the problem didn't say what is mu1, what is mu2, because unless you said it, you never know what it should be, right? And then the hypothesis. And then the hypothesis is R. You would have a H naught and a H alternative. H naught can be written as mu1 equal to mu2, or mu1 minus mu2 equal to 0. This is the same. And mu1, mu2, which sign should we put left? Less than, greater than, or not equal, right? What we wrote it down here is dynamic less or equal than static. So less than. Another form would be mu1 minus mu2 less than 0. So in the book, they used this pair, but it really depends on you if you want to use the second pair. They're all the same and they're correct. That's step 1. Step 2 is identify alpha. According to the problem, alpha equal to 0.05. Step 3 would be calculate the test statistics of t, which in our case, t equal to x1 bar minus x2 bar divided by s1 square s2 square divided by n2. Simply plug in numbers and then use your calculator. And I've showed you that trying to plug everything together so that we can reduce the bias when we're doing the calculation. You don't need to run it up when we calculate. That will help, but it just depends on you. If you have to, or say you get used to use calculator and then you say, I have to run it up every time we do calculation, it's fine. Keep do it. Just try to run it one more decimal places than they required. So this is what we've got. The negative 2.681 is your solution for the step 3. Okay. And then step 4, you'll have 2 methods, right? Critical value approach. Critical value approach. In this case, what you would have is because of our left-tailed, right, less or equal than sign. So we will have a left tail plus. And the value we've got, this is our T0. Your T0 is negative 2.681. Just keep it there. We're not use it for now. What we will use is trying to find the critical value with the area under the curve of the left side hand of our t-score is alpha, and alpha equivalent with 0.05. And what is the t alpha? Okay, now becomes familiar, but again, a little bit complicated, because remember, when we're using t-scores, we have to know the degrees of freedom. And in our non-pooled t-test, non-pooled t-test, your degrees freedom now equivalent with capital delta, it is equal to S1 squared over N1 plus S2 squared over N2. Entire thing squared divided by each of them square divided by N1 minus 1, and then S2 square N2 square divided by N2 minus 1. It's just so complicated. And then carefully when you input your numbers. So what we've got for S1, we've got S1 right here, right? S2, and then oops, and then N1, N2. So plug everything inside. We have 84.7 squared, and then a 14 is my N1. 38.2 squared, a 6 is my N2, and then entire thing square. So whatever we have, keep it the same for the first term. My divided by 13, right? 13 comes from 14 minus 1 plus, okay, write it down what we had, over a 5. So this 5 comes from 6 minus 1. You can get your degrees of freedom when we write it down. It would be 17. So remember here, we're going to round down. Okay. So 17 now is my degrees of freedom. Let me put a 17 here. And now you go back to the table. Okay, remember what we've had. I will switch to the computer itself to show you the table where it is. Okay, 17, and with degree of freedom of 0.05 on the very left hand side, and this thing would indicate, because when we're using the table for t-table, you would have something on the right side instead of the left. So it's the same thing, degrees of freedom equal to 17, with the area 0.05 on the right side, and we find what is the t-scores. Okay, so back to the table. I have uploaded a t-table, more accurate one, on Blackboard, so you can download it. Or you're welcome to use any software or website which indicates your more accurate t-scores. So remember what we've had. The alpha is 0.05. So the second column, degrees of freedom is 17, this row. So which we've got is, let me write it down on my report, 1.740. That's my t-scores. Okay, back to the pad. Okay, I've just wrote it down. The 1.17 is what we've got for the T70. Sorry. So that's the t-scores And we know this is the right side. And essentially what we need is a left side area. So this question mark indicates it should be a negative 1.74. It looks so messy. I will write down in black what we've got. Seems my pen is out of battery as well. The same as my 19% battery for the pad. Okay, however, what we've got for the negative t-score with degree of freedom 17, this would be negative 1.74, right? So even though we do not have a negative table, but you could always find a positive and then flip it because of the symmetric property at a negative sign. So now this is my critical value. And what we've got, T0 here, right? T0 here is negative 2.681. You're going to put that number into the plot. A negative 2.681 is definitely on the left side of your negative 1.74 because it's smaller than that. So your region, so your T0 line within our rejection region. Because of that, you're going to reject H0. So this is the conclusion that we will draw from the critical value approach, combined with the next step, interpret involving with all the informations. That is a complete of a non-pooled T hypothesis testing. We'll try another way. On the second p-value approach. Similarly, on our draft, again we would have a left-tailed plot because this comes by our hypothesis test, right? The hypothesis test, left side. And you're going to put T0, the negative 2.8681 at here. And now I'm trying to find the p-value using the table. Again, according to the same delta degrees of freedom, we will run it down and get 17 as your answer for degree of freedom. So let's just directly keep it, write it down here. It will be 17. Okay, now remember those two words. We'll go back to the table and find where is our p-value is. Okay, so our degrees of freedom would be 17. And we'll look at this row, all right? And then the value we've got is 2.681 negative. You're going to look at the absolute value of it. So positive 2.681. Okay, this is 1.3, 1.7, 2.1, 2.5, and 2.8. And our number something around 2.6 would be inside this interval. Should be here, right? And then you look at the alphas. It's 0.01 and 0.005. That means my p-value. So you're writing according to the table. even though I couldn't find an accurate p-value, but your p-value should locate between 0.005 and 0.01. Okay, so I have just wrote it down. The fact that I've just, when I wrote it down. According to the table, you would have p-value greater than 0.005 and also less than 0.01. That's my p-value. And back to my alpha. Alpha is 0.05, right? 0.05, my alpha, step 2. This is definitely less than my alpha. Oh. Okay. Alpha equal to 0.05 and 0.01 less than 0.05. So we would have p-value less than alpha. Remember the criteria? You reject H0 if and only if your p-value less or equal than alpha. Right, so this gives me the conclusion of reject H0. Okay, and the both actually lead the same results, rejection and rejection. So hence, we've finished the non-pool t-test approach. So another thing I want to mention is, according to this, we could also figure out the confidence interval, right? And if you remembered, the confidence interval formula it is x1 bar minus x2 bar plus or minus p alpha over 2 times s1 square over n1 plus s2 square over n2 with the same degrees of freedom delta. Okay, that complicated one, the formula here, delta. Okay, so according to this, it is easy for us to figure out the same thing. Okay, we have x1, x2, s1, s2, n1, n2 according to the information given from the problem. Oops. Here. And the only thing different is the t alpha over 2, which we'll find from the table. So that is t alpha is 0.05 divided by 2. Degree of freedom, I can move it. This is delta. Degree of freedom is 17. Now we could use the table. So I've checked it out. I don't want to switch the screen again, but what we've got for this one should be 2.11. Okay, you're welcome to check it. So 2.11 is your t-scores. You're going to plug this inside, and then everything else that keeps the same. So basically, just plug every numbers you've got in the formula, and this plus or minus give you the left side point and the right side point, and hence you will get a confidence interval. Okay, so that's close the 10.3 thing. Okay. So I had example, and then the confidence interval. And then in the next class, we're going to continue with 10.4. But yeah, I'll see you in the next class.